Engineering 305. This is chapter 6, sections 1 through 4 on the torsional loading of shafts. The course learning objective is we're going to calculate stresses and deflections which result from torsional loads on round or rectangular solid sections. Now, if you're in my section, we do round and rectangular. Professor Hahn, I know last year did not cover rectangular. It's one extra section at the back of this chapter, but it offers an insight into why round shafts are what we use, and they're just much more effective. And so that's why I cover those. Anyway, let's look at the equations from the study guide. We have the material property, which really came out of chapter 4 there. And then we've got our equations of stress, which as the shear stress there and there. And now I'm just going to point out, and this is similar to what we did in chapter 5 with pressure vessels, this rho represents a radius. They just love it. They just love it. Just eat that up. But really, we need that function. This is the one that I want to say, pretty much interested in. We need this in order to integrate a function. We come up with a geometric property called J, the polar moment of inertia. That is, it's just a definition, and we will explore that. That comes out. It's an integral, and it's an integral, so I don't like it. But that's okay because we come up with an equation. We integrate that, and for round circular sections, and it's fine. It's fine. Lastly, this section we're going to talk about deflection. That's actually section 4, and we'll be talking about deflection and how we calculate that. So this is for torsions. This is the equivalent of the deflection is equal to PL over AE. And so we will talk about that later. That's not something we need to jump into quite yet. So first things first, and I kind of told you before that stresses weren't real, and I hope I didn't burst anybody's bubble on that, but I'm going to tell you that torque is real and that torsion is real, but that moments are fake. And that kind of a moment and a torque is hard to separate at times, but moments are fake. A moment is the result of a force applied at a distance. You can't apply a moment, you can only apply a force. So when we talk about problems where we're going to go, yeah, and we applied a torque or we applied really a moment, no, we didn't. We didn't do this. Instead, what we did is we applied a force here and a force here, and the force times that distance from the center, call that R, and then I have to multiply that by 2 because there are 2 of them. That is what equals, that's an equals on a corner. That torque is equal to 2FR. It's kind of a little detail, but these are the things that if you just accept everything as real, it's okay, but it's really a construct. It's a mathematical construct that we've made in order to help us face the world. And so you can't just apply a moment. I think that's a big deal to understand. I hope that helps you with some of this. So first things first, and I kind of told you before this, stresses weren't real, and I hope I didn't burst anybody's bubble on that, but I'm going to tell you that torque is real and that torsion is real, but that moments are fake. And that kind of a moment and a torque is hard to separate at times, but moments are fake. A moment is the result of a force applied at a distance. You can't apply a moment, you can only apply a force. So when we talk about problems where we're going to go, yeah, and we applied a torque or we applied really a moment, no, we didn't. We didn't do this. Instead, what we did is we applied a force here and a force here, and the force times that distance from the center, call that R, and then I have to multiply that by 2 because there are 2 of them. That is what equals, that's an equals on a corner. That torque is equal to 2Fr. It's kind of a little detail, but these are the things that if you just accept everything as real, it's okay, but it's really a construct. It's a mathematical construct that we've made in order to help us face the world. And so you can't just apply a moment. I think that's a big deal to understand. I hope that helps you with some of this. So let's think about twisting a shaft or a pencil or a pool noodle, wherever you've got, and you grab onto that as big, and you wind up doing a twist. And if we did it with a pool noodle or something soft, we give it some twist, and you can see these lines start to curve as that starts to deflect and move and work around. And if we would cut that someplace, let's cut that someplace in the middle, right? Or we'll cut it closer to the end. But then once we've cut it, we got to keep thinking about it. And what we're going to get now is, here's one end, and as I'm twisting, this is right, and this is twisting, so my torque is here, and this one is going this way. And so inside the material, if I looked at a little square like we had in chapter 2 or 3, there would be a little force going this way. And if I draw another one, I've got it going that way. And I need to draw it at different radiuses. But wherever I would draw, I would have these little forces, and they're shear forces. And on the other side, they're going the other way. So if you wondered why I said I'm not too really incredibly excited about your sign choice, well, because if I look at this cutting plane this way, I get positive, and if I look at it this way, I get negative. So I'm not too excited about the sign choice. So that's what we get, is we get this little distribution over the whole end of all of these shear forces. And then what I would like to do, if I want to figure out how much torque is in the system, I hate saying it, but I have to integrate. So I'm going to come up with an equation, well, let's go to the next slide where I've got some whiteboard to work. I'm going to come up with the torque. Oh, we need a better color than that. All right. The torque is equal to the integral of all of these shear stresses. And if it's a stress, it's got to be multiplied by an area. But it's a torque, I've got to give it, it's a force and a distance. So it's a shear stress, the radius, and the area. Now, if you're looking in the book, if you're playing along, if you say, hey, I'd like what Tübingen does, but I get a better education from the book, they're going to put that, they're going to write that as torque is equal to the integral, not delta. Torque is equal to the integral of shear rho dA. Why? Because that's their radius, because they are just, there's some people who just want to be something they're not. I think they wanted to be Greek. I really think they did. But we're not gonna use that. We're gonna use a R, because that seems to make more sense. But now, if we're gonna integrate that, we need to know. I'd love to move stuff outside the constant or outside the integral, because I need to know what the shear stress is as a function. I need to know that as a function of R and theta, because that's really what I'm integrating over, this this dA, right, is going to be equal to an R dr d theta. That's going to be the easy way to integrate that. I don't want to do an xy and write the circular function. So I need to come up with an equation there. Got any suggestions? So if I want to start deriving or working our way towards some equation, the first thing I'm going to do is I'm going to look at this circle, this face of this thing, and I'm going to say, look, I've got a little element of stress here, and I've got one here, and I got one here. And I drew these all so that they're all at the same radius. They're all at some fixed radius, R1. I don't just want to call it R1. So I'm going to use R for other things. And maybe that's why the book uses rho. But there you go. And the first thing I do they change? Is this strain, is the stress going on here at A, is it different than the stress at B? Is it different than the stress at C? If they're all at the same radius? And the answer is no. Or it's an assumption. I am going to assume that this is axisymmetric. I'm going to assume that that's axisymmetric. Is it? I don't know. But that's what we're going to assume. Later on, scientists and engineers are going to prove that it's a good assumption. But when we started this, it was just an assumption. So we had shear was, we were working on shear as a function of R and theta. And now we've said, nope, no theta. And so it's just equal to a function of R. And if we get that, then we can integrate. So here's our shaft or our cylinder, and we're twisting it, right? We got this twisting motion. And so that twisting motion, I start here, and as you saw those lines, this thing slowly warps. And this is my shear distance from B to B, from B to B prime. That's where that moves. That is the delta in the S direction. And here's L. And if you remember, they're using the same symbol that they used in chapter 3 to define the strain. That's that strain, that's that angle, which is which we're coming back to. That's our shear strain. Gamma is equal to delta S over L. But we've also got this, what we really want to know is how much did this twist, this theta here is the twist, and that's important to us. And you can look at that theta, that distance B to B prime. If I look at it from the end, here's where B started, here's where B prime ended, and that angle, keep that going, there's my theta, just doing the same figure but now an end view. So this distance delta S is equal, it's also equal to theta times R, but we're not going to call it R. We're not going to call it R. We're going to call it a different, we're going to call it C, where C is now, I'm going to call it the distance to the extreme fiber. Got to make space for my face there. Yeah. So, all right. That's the distance to the extreme fiber. That's the farthest point away. And that's how far, that's the total angle. That's the, it is the radius, it's the radius, but it's not R, the variable, because we're going to need R, the variable, later. So that's why I've given it, it's a constant. It's a fixed distance. All right. So now let's go throw together some equations, and then we're going to start manipulating them a little bit, and we're going to see how this all works. And we have one more assumption to make. So let's start putting some equations down. From chapter 2, and we just had this, that total strain is equal to delta S divided by L.
And that's that important equation that defined what that shear strain was. And then what we just had was delta S is equal to that twist in the system times times C, that distance to the extreme fiber. And so what this allows me to do, we can combine those two things, and we can say that our shear strain at C, all the way at the extreme fiber, is equal to the twist times C divided by the length L. And so that gives us, this is starting to put together, this is the strain at C, but really I need, and you'll see, I want the strain at R, at any R. Well, when we put this picture together, and I drew this deflection, I drew this deflection, here's the line that started and here's where it went, and that was my delta S. You see that? I know you can't really tell. It's linear. And that's an assumption. We assume that this is linear, and we assume one other thing, and that it's planar. And those are good assumptions for a circular section, but otherwise they're not always good assumptions. So, but that's the assumption that we're making for this, and it's true. It's been shown to be true for a circular section. But now we can look at this. The strain at any position is a function of, it starts at 0 and it goes to that value that we had up here, theta at C, or gamma at C. The strain at C is equal to theta C over L. So now I'm going to rewrite, I'm going to change that to be that the strain at R is equal to the strain at C times the radius, whatever radius I'm at, divided by C, and that's the distance to the extreme fiber. Now, I got to be careful here. I'm going to put this in a different color. This is a subscript, not that. I then need to go substitute this in. So this is going to be, I don't like that color. Then that is going to be theta times C divided by L times R over C. Or I could put the C over here to make it look like this equation, but it doesn't matter. Get the red back out that I don't like. That's going away. Those cancel. So now you've got gamma at any radius is equal to theta over L times R. Sorry, theta, yes. That's that's what I need to work with. All right? And actually, I'm also going to leave that we're going to use this equation too. Gamma at R is equal to gamma at C, R over C, because that'll actually make our derivation go better. I paused it to look at a couple of the next steps. So now we'll continue on. We're going to go back now to our integral. I hate to tell you that, but we're going to go back to our integral. So where we left things a long time ago, we had the equation for torque, and that was that the torque is equal to the radius times the shear stress dA. That was the integral that we needed to solve. That was integrated over all of the area. And now we're in a position to start looking at, because I have shear as a function of R and theta. And you're saying, no, we don't. We have gamma as a function of R and theta. You're right. But I'm going to go back to, I'm going to erase this. I'm going to go back to a basic definition that we have from chapter 4, and that is that G the shear modulus is equal to the shear stress divided by the shear strain. And so if I have G, which is a constant, and I know gamma as a function of R and theta, then I know the shear as a function of theta. So shear as a function of R and theta is equal to G times, isn't that kind of cute, G times gamma, which is a function of R. Well, it's not a function of theta because we said it was a constant, but we still get the idea there. That's kind of sloppy, but I got it. So what did we have for our shear equation? Well, our shear as a function of R is equal to G, or sorry, then our shear is the shear at the extreme fiber times the radius divided by C. Now I am in a position that I can drop that in and start integrating. Torque is equal to the integral radius G gamma at the extreme fiber C times R over C dA. Now, what's a constant? What's a constant? G is a constant, and gamma at the extreme fiber is a constant. That's why I wanted to leave that in that format. And I've got C as a constant, but my R is not. So now I've got a new, I can rewrite that equation is equal to G gamma C divided by C times the integral of R squared dA. Now, that is a special term. That right there. You are used to doing second moments of inertia. Let's swap over to the next screen because I need more space. You are used to doing second moments of inertia. You've done these in calculus all the time. We do the expected value where we integrate x and then over all values and then we divide and we get an expected value. Well, this is the second moment of area, but it's the second polar moment of area. So it is J is equal to the integral of R squared dA. And that's a special value, and it shows up all the time. It shows up in all of our torsional problems. And so we gave that a special name. We gave that a special, but in mathematics, we have this thing for the first moment, for the second moment. And so I know that's not, you didn't want to do the math, but we just call this J. And now for engineers, we're able to look this up in a table, but we would integrate this, which it's the double integral from 0 to 2 pi from 0 to r of r squared r dr d theta. And so that is going to give me an r to the fourth over 4, right? R to the fourth over 4 times the integral from 0 to 2 pi of d theta, which is going to give me a 2, so it's an r to the fourth pi r to the fourth over 2. Yeah, and the way you'll see that most of the time is pi over 2 r to the fourth. That's cool, kind of. It breaks this term out so we don't have to deal with it at the same time we do everything else, all right? So, so now that we've got this geometry defined, we can go back and take a look at our equation again. So 2 slides ago, we had this equation, and then we stopped and had this little distraction where we defined this to be equal to J. But now we can rearrange this and we can get back to, we can get one of the major equations that we've got. And I'm going to write it this way at first because that's the way that translates. But now let's take this term and replace it back with tau. So I'm going to have tau at C, and that's going to be the maximum shear times J divided by C. And this is the big stress equation that I'm going to have in chapter 6 when I deal with torsion. That I the torque is equal to the shear stress, the maximum shear stress, times this J for the cross section, divided by C, the distance to the extreme fiber, which you could also think of as the radius, the maximum, the largest radius. That tells us that's an equation between the force and the stress. And that's a biggie. That's a biggie. Let's get rid of that line so that's a little more clear. All right. Now we're going to take that. We're going to go one step farther, get the other equation that we're interested in. The other thing that we're interested in is the displacement equation. And so we'll go back to where we were. I had this equation that the strain at any radius is equal to, well, really, I don't want, yeah. I want that strain at any radius is equal to theta r over L. And then I'm going to rearrange that so that I'm going to mix it up so that I get theta, because that's really my displacement now, is equal to gamma at r times L over r. And of course, now I'm going to replace that. I'm going to replace the gamma with, that's the shear stress, R divided by G, and then I've got an L over R. And then I know from what we just solved on the previous slide that the shear stress, I have to rearrange it, but that's equal to T R over J. The torque times the radius divided by J, that polar second moment. And now I can substitute that in. And so then I'm going to get that theta is equal to, well, I'm going to put tau, T R over J, and then I'm going to L over G, and I've got lowercase r and uppercase r, and I really should have been consistent. It's an lowercase r and G and an R. And so then my R's cancel, so that didn't matter. And then I'm left with TL over JG. Now, two equations, and I want to talk about them, and I want to develop that a little bit. So let's go to the next slide. So as a recap, we've got two major equations that we should be walking away from, and I'd like to give you the equation numbers from the text. Here we go. The first one that we've got is that the torque is equal to the stress times J divided by C, the shear stress times J divided by C. That's our first major equation. That is equation from the textbook. It's equation 6.6. Took us a couple things to get there, but we started with the fundamentals and we got to that. And then the other equation that we've got is theta is equal to TL over JG. And this is equation 6-7. Now, if I had, let me looking at my notes. I didn't do it. I jumped right into the next thing is the example problem, right? But I want to go look at what we've done here, and now I want to draw parallels back to chapter 5. In chapter 5, we had an equation that related our forces and our stresses and geometry. And that was the stress was equal to force over area. This time I don't have the equation written like that. But I could have written the stress is equal to TC over J, which is simply a different way of expressing it. But now what you're looking at is this is my stress. This is my stress. I've got a force, obviously. My torque is a force. And then the tricky part. This is geometry, where this has two terms for geometry. Not terrible, but there are two terms now for geometry. But otherwise, I've got these parallels between stresses, forces, and areas. And I will say this, as my area increases, this is actually, so this is an area squared, and this has got units of, right? J is units of to the fourth, and then I've got a C here, so that's a unit, and this has got units of length, so that's going to cross out one, and torque has a unit of length in it, so that crosses another. So that's giving me, I'm canceling two of those, all my units work out. But you can see the parallels now between chapter 5 and chapter 6, and they don't end there. Here is my equation for displacement. Now, I hope at this point you have it memorized, but from chapter 5, the equation for displacement, PL over AE. And so I'm going to use the same color code kind of. This is my force here, this torque. That's my force, this P. I've got geometry terms. The length factors in. Why? Because if it's longer, it gets softer. Sorry, I don't want to use that color. I'm going with geometry terms are in purple. So that's a geometry. And that length shows up on the top in both. I think that's interesting. J and area, again, geo. And then I've got my material property. This is the stiffness. Sorry, I got to get a better color. Going with red. This is my material. So by looking at those equations that way, what you're seeing is you get this parallelism between deflection, radial deflection, twist, which is a result of a torque, and there's the parallel to the axial deflection, which is a function of that force. And then the longer that your part is, the more that it stretches, the more that it twists. The stiffer that your material is, that's in the new denominator. The stiffer that it is, the less that it twists. Excuse me, hold on. And then your area, if I throw more geometry, if I throw more material at it, whether that makes for J to be larger or for the area to be larger, that decreases the deflection, the twist, or the stretch. So these equations function and look similar. Similar. All right? Those are our big equations. If I get rid of all my scribbles, those are the big equations that we've got to deal with actually from chapter 5 and 6. The two big equations that you're seeing, equation 6.6 and 6.7, are the ones that we're going to wind up using predominantly all the way through chapter 6. So we'll add a couple, but that's the heart of chapter 6 right there. One lecture, all of 35 minutes, but that's okay. And then we get some example problems to do. Example problem 6-1 is the first one we're going to do, and I'll decide if I do more after that. These are fairly straightforward. The derivations are a little harder to get to these equations, but and J is a different concept than you're used to. But the example problems are fairly straightforward, and with your skills in math, you should cut right through it. So hope you're doing well, and there's more to come.